Hi everyone. In this video, we are going to discuss about an interesting topic from number theory. The topic is that how to determine if a given number is a prime number or not. In the junior classes, many times we may be asked to write an algorithm or maybe write a small little program to input a number from the user, meaning to take a number from the user and then go through some algorithm or some logic to find out whether the number is a prime number or not. And if it is a prime number, we need to display it on the terminal that yes, it is a prime number, or maybe it is not a prime number, right? Now, for that kind of algorithm, what we need to do then? Let's take an example here and we'll see what we need to do. So first, let's take an example. Suppose we take an example of, say, number 36, right? And programmatically, we have to write an algorithm to check for the primality of this number, whether this number is a prime number or not. How are you going to do it? Well, if we write a program like this, the program will first check and try to divide this number by 2. So we start from 2 and we try to divide it. If we get no remainder, then we know that this is not a prime number because it is greater than 2, but it's divisible by 2. That means it is not a prime number. Here is a number which is 2 or another prime number that divides it, right? And similarly, we can try with 3 and then 5, and we can try with all of these numbers, right? Or even we can go like this. So we start with 2, then 2, 3, 4, 5, 6. We just keep on, trying with every positive integer starting from 2, right? So that way, yes, we can keep on doing it, and finally we'll be able to figure out whether this number is prime or not. But do we really need to check for all these integers up to 35? Do we really need to go all the way up to 35 to confirm whether a number is prime or not? Now, if we give you another crazy looking number, suppose I give you a number 41. So if we take this example of number 41, because for 36, you see, we can easily find it. As soon as you divide by 2, we can prove that yes, this is not a prime number. How about let's take a number 41. So if we take a number 41, which you know that it is a prime number. So now to test for primality, do we really need to start at 2 and then go from 2, 3, 4, 5, etc. all the way up to 40? The answer is no. Why? Because we're going to prove that. But how far do we need to go? Let me first tell you how far do we need to go. Well, we need to go up to, so we start at 2 and then 3, then 4 and then 5, and we need to go all the way up to the integer which is less or equal to square root of 41. Now, what would be the square root of 41? Well, 41 is between 36 and 49, so it will be between 6 and 7. So essentially, we need to go up to 6 and we should be done. So if we go up to 2, 3, 4, 5 and 6, we should be good. We should be able to prove that yes, this number is not a composite number, it is a prime number, right? None of these integers would divide this number. That means this number will be a prime number. We can declare that yes, this is a prime number because we have checked from 2 up to the square root of this number. For each of these integers, we have done the division, we have checked, and none of them seem to divide this number 41. That means 41 must be a prime number. It cannot be a composite number. Now, how are we going to prove that hey, every composite number must have a factor which is less than or equal to its square root, right? So let me write it down first. So this is the theory here that every composite number or any composite number n must have a factor which is less than or equal to its square root, and we have to prove it, right? So now let's assume that this composite number n has two factors, let's say a times b, and also let's assume that each of these factors are greater than the square root of n. Now, why are we doing it like that? Because the proof has to be done via contradiction. There is no direct proof, we have to do it via contradiction. So we are going to take a contradictory scenario here. We are going to assume that hey, a is greater than square root of n and b is also greater than square root of n. And then let's see what happens. Because if we then come to a situation where it contradicts our initial assumption, and by the way, this is our initial assumption that n is nothing but a product of the two factors a and b, and then with that assumption and this other assumption here, I underline that with this assumption, we're going to see what happens. Now, if we multiply these two inequalities, the a greater than square root of n and b greater than square root of n, let's see what we get. If we multiply both of them, we can say, okay, then a times b will be greater than square root of n times square root of n, which is square root of n square pretty much. So you can say, okay, from here we can say, well, then a times b is actually greater than square root of n times square root of n, that would be n. Well, that kind of contradicts. So now I'm going to highlight this in red, that this kind of contradicts our initial assumption. Initially we assumed that a times b is equal to n, but here we come to a situation. So now I'm going to show you like this. So here we come to a situation where it kind of contradicts our initial assumption. So this is a contradiction right here. That means our assumption is not right. Now, what were our assumptions? Well, n equals a times b, that was an assumption, and also we had this other assumption where we assumed that a is greater than square root of n and also b is greater than square root of n. So for those two assumptions, we now come to a situation where it seems kind of odd, right? Meaning a times b now greater than n, but we assume that a times b is equal to n. So this is the contradiction. So that means our assumption that a is greater than square root of n and b is greater than square root of n, that assumption is not correct. So that was a wrong assumption, and I'm going to write that down, that this was an incorrect assumption. So this was a wrong assumption. I'm writing on the side here. So that was a wrong assumption. Alright. Now if that was a wrong assumption, then what we can say about it? Well, we can say that both a and b cannot be greater than square root of n at the same time. That means one of them must be less than or equal to square root of n. That is the part we need to clearly understand, that our assumption was a is greater than square root of n and b is greater than square root of n. We assume that both a and b, each of them are greater than square root of n at the same time, but that assumption has been proved wrong, right? So then we have to say that, okay, then either a is less than or equal to square root of n or b is less than or equal to square root of n. So I'm going to write it here. And as you can see, this clearly indicates that n has a factor, whether it's a or b, n has at least one factor which is less than or equal to its square root, right? So that's very clear now. When the equality will happen? Well, the equality will happen when n is a perfect square, because if a is equal to square root of n or b is equal to square root of n, then what happens? Well, let me just go with a then. So we can say when a is equal to square root of n, then guess what? Then from here we can say, well, then n must be a squared. That means n is a perfect square. So the equality happens when n is a perfect square. Similarly, we can do the same thing for b also, that b would be equal to square root of n when n is a perfect square. So just doing it with a is sufficient. We really don't need to do the same thing, or don't need to write the same thing for b, because we are just focusing on at least one factor which is less than or equal to square root of n, and that's exactly what we are supposed to prove. So this proof right here, this is sufficient condition to prove the theory that yes, if n is a composite number, then it must have at least one factor which is less than or equal to its square root value. Now if we take an example, let's say suppose we take an example again. Say suppose our example is 36. Now can we write it as like this, say 1 times 36? Yes, those are the two factors there. Also we can write it as maybe 2 times 18. Sure, we can write it as 3 times 12. Of course we can do that. We can write it as 4 times 9. We can write it as 6 times 6. Now is there any other combination? So we don't see any combination where both factors are greater than 6. Yes, we do see a combination where both the factors are equal to 6, but we do not see any combination where both factors are greater than 6. That combination is not possible, because we have already proved that it must have at least one factor which is less than or equal to its square root. And we can clearly see that from this example. And also another thing to notice is that we have a combination of factors where each of the factor equals the square root of 36. And the equality happens when 36 is a perfect square. And in this case, we know that 36 is a perfect square because it is a square of 6. And because 36 is a perfect square, we can also find two factors here, which is 6 times 6, two factors which are equal to its square root. Meaning each of these factors right here, this 6, or this other 6 also, you can see that they are equal to square root of 36, each of them, right? Each of them, not the entire thing, of course. This each factor equals square root of 36, and the equality happens when this composite number 36 is a perfect square. I hope everything made sense so far. Thank you for watching. See you in the next video.